Hey everyone, Mr. Shatter here to talk about separable differential equations. The idea of this video is to integrate functions involving two variables, so integrating a function involving an x and a y. So separable differential equations, the goal is to put the y's on the same side as the dy and the x's on the same side as the dx. The idea is to take a simple differential, whatever it is, and treat the dy and the dx separately. So by multiplying by dx on both sides, you can actually cause the dx to eliminate from the left side and move over to the right. Your job is to get the y's on one side with the dy and x's on the other side with the dx. Last thing, when you integrate both sides with respect to each variable, so the left would be integrated with respect to y and the right with respect to x, you technically would need to write 2 plus c's, but just for the sake of argument, knowing that a constant moved over to the other side would still yield a constant, we actually only ever write plus c on the x side, okay? We don't write a plus c on the y side and the x side. Let's try an example. So example 1 says solve for y, the original solution, if dy dx is xy quantity squared and y equals 1 when x equals 1. Okay, so obviously the idea here is to take this differential, and I'm going to rewrite it as x squared y squared, just distributing the exponent. And the goal is to isolate the variables and integrate it. And so what I'm going to do is I'm going to actually multiply both sides by a dx here. Multiply both sides by a dx, and on this side that cancels, leaving me with dy equals x squared y squared dx, and then divide both sides by a y squared, leaving me with 1 over y squared dy equals x squared dx. Your job now is to integrate both sides with respect to the variable that's there, like the left side with y and the right side with x. Let's go ahead and try that. So the left side is y to the negative second. So if I integrate that, I get negative y to the negative 1 equals, and then integrating the right side would just yield x cubed over 3 plus c. Remember from the previous slide, we're only going to put the plus c on the x side, okay? Using my initial condition 1, 1, I'm going to put 1 in for y and 1 in for x, which will yield c is equal to negative 4/3. So then right in this step, I'm going to go ahead and put down that c as negative 4/3. So negative y to the negative 1 equals x cubed over 3 minus 4/3. All right, and now I'm going to isolate y. So let's see if I can add a page here to do that. Add a page. So if I need to isolate y, that means I should probably take these right terms and put them over the same denominator. So it would actually be negative y to the negative 1 equals x cubed minus 4 all over 3. Then we multiply everything by negative 1, okay, which would just yield y to the negative 1 equals, and then this is now just swapped signs. It's like negative x cubed plus 4 over 3. And then I just need to raise everything to the negative first power, which would reciprocate, leaving me with y is equal to 3 goes on top, negative x cubed plus 4 goes to the bottom. So this now is the solution to the problem that that this differential was solved for at 1, 1. Let's try another one. Example 2. Find the particular solution of dy dx equals cosine squared y and y equals 0 when x equals 0. So for this one, I'm just going to write down the differential. So this is cosine squared y, and I want to get the y over with the dy. So if I multiply by dx, that'd be dy equals cosine squared y dx. And then if I divide by the cosine squared y, I'd have 1 over cosine squared y, which is just secant squared y, dy equals dx. There's nothing over there anymore, it's just a 1. I'm actually going to put a 1 there. It's helpful to write the 1. I'm then going to integrate both sides with respect to the variable that is on that side. I know the integral of secant squared y is tan y. And I know the integral of 1 is y, or x rather, because I'm differentiating with respect to x this time. And then I'll add the plus c on the x side. I'm then going to use the point 0, 0 to get tan of 0 equals 0 plus c, so c is clearly 0. So then I'm going to go put that back in. Tan y equals x plus 0, which is just x. And solving for y, I just need to apply an inverse tangent. Tan inverse both sides, get y equals tan inverse x. Okay, so this is the solution passing through 0, 0. Example 3. Find the particular solution, dy dx equals e raised to the x minus y at x equals 0, y equals 2. So let's rewrite the differential. dy dx equals e to the, and I'm actually going to rewrite this, e raised to the x minus y is actually just e to the x over e to the y, using my exponent rules. And now I could multiply both sides by dx and by e to the y, or just simply cross multiply. That's kind of the same thing. So I'm actually going to get e to the y dy equals e to the x dx. I'm now going to drop an integral both sides, Integrating both of them is just going to yield the same thing, e to the y equals, and then e to the x plus c. And then I'm just going to solve using my initial condition, 0, 2. So e to the y is going to be e raised to the y is 2. E to the x is e to the 0 plus c. E to the 0 is 1. So c is equal to e to the 2 minus 1. I'm then going to put that in there, in that above equation. So e to the y equals e to the x plus c, which is e to the 2 minus 1. And then I need to get rid of the e to get y alone, so I got to ln everything. Take natural log of everything. So natural log of e, I'm not even going to write it on the left side because I know natural log of e, they wipe each other out, giving me y equals. And then the right side is just natural log of all this stuff. I'll put absolute value, e to the x plus e to the 2 minus 1. And this is my solution.